Okay, this is gonna be for the yagi. So for those that are doing this problem, um, so so it's a 7-element end-fire yagi antenna shown below. So the frequency of ovulation is equal to 600 megahertz. The distance between the driven dipole and the reflector is 0.1, and between the driven and the dipole and the directors is 0.115 between the different directors. We will study that and find it out. Okay, so so this is what we have. We have an antenna and a yagi that has a reflector. It has 1, 2, 3, 4, 5, so on 5 directors. Okay, so let me draw this in cleaner. So we're gonna take the X, Y, and Z. So this is gonna be the XY plane, YC plane. Okay, so this is gonna be C. Oh no, actually this is gonna be the XY. Okay, so so I'm looking for on the top. So this distance right here, okay, so we know the distance from here is 0.1 lambda, 0.15 lambda, 0.3 lambda, 0.45 lambda, 0.6 lambda, 0.75 lambda. Okay, so this is the driven element, and these are the directors. This is the reflector. Okay, so in order to calculate let's start by naming the R1. It's equal to minus 0.1 lambda. So this is distance right here. R2 is equal to 0 because it's the distance from here to 0. R3 is equal to 0.15 lambda. R4 is equal to 0.3 lambda. R5 is equal to 0.45 lambda, and R6 is equal to 0.6 lambda, and R7 is equal to 0.75 lambda. Okay, so the first question it asks us, we assume that the driven dipole has a current of 1. So this has a current of 1. Okay, so this can be told like the current for each one of them. So a driven dipole has a current of 1. So we need to calculate the phases on each dipole element so that the antenna has a maximum in the forward direction. So we're looking for a forward direction in the y direction, so it's gonna be something like this. So we want to have a maximum in this direction. So we can assume that the reflector, which is this one, and the first director have a current of 0.9. So this one has a 0.9, 0.9, and then each of the directors has a 0.6, 0.6, 0.6, 0.6. Okay, so they have those currents. Okay, so then we need to calculate the phases for each one of them. So in order to calculate for the phases, what we're gonna do is we're gonna say that the array factor is equal to the summation of I equals 1 to 7 I0 e to the j beta 1 times e to the jk ar I ay. So this becomes I equals 1 to 7 I10 ej beta 1 beta I plus k ri sine theta sine phi. Okay, so this term is gonna be called y this symbol right here, phi I. Okay, so so in order to have a maximum in this direction, all these terms, so we're gonna have the summation of all these terms or vectors, and in order to have that, the AF peak, AF, in order to have a maximum, this one has to be equal to 0. So that becomes equal to 1. So you have a maximum direction. So if we take that into case, then what we end up is we're gonna create each one of these. It's gonna be equal to y1 to b1 plus k r1 sine theta sine phi. For the next term, it's gonna be y2, it's b2 plus k r2 sine theta sine phi. Okay, and then y3 is equal to b3 plus k r3 sine theta sine phi. y4, y5, y6 and 7. Okay, so these are gonna give you, okay, so we know these terms are gonna be equal to 0. So then in that case we have to solve, if that's equal to 0, then we have this equation for beta 1 is equal to k r1 sine theta sine phi. Okay, k, it's gonna be coming from k is equal to 2 pi divided by lambda. That's the k number. Okay, so for this, v2 is equal to k r2 sine theta sine phi. Okay, and the same for b3 and up to b7, k r7 sine theta sine phi. Okay, if you keep going through this list, then you end up having, you'll find out that uh, the phase angle for the first one is equal to B1 is equal to 0.2 pi, B2 is equal to 0, there's no phase, B3 is equal to minus 0.3 pi, B4 is equal to minus 0.6 pi, B5 is equal to minus 0.9 pi, B6 is equal to minus 1.2 pi, and B7 is equal to minus 1.5 pi. Okay, so these are the phase values that you need to figure out. So once we have that, then we're gonna have our equation that's gonna be the summation of all these terms the summation of all these terms, which is gonna be, so it's the AF is equal to the summation of I equals to 1 to 7 I O e to the j beta 1 plus k r1 sine theta sine phi. Okay, so in order, we know that the radiation pattern is gonna be in this direction. On the forward on the plus y, and there's gonna be a minimum backload on the minus y. So in order to have the peaking forward, in the plus y, we're gonna have theta is equal to pi over half, and phi is equal to pi over 2. So because okay, so in order to have the peak forward is gonna be in the positive y. So in this case is phi is equal to pi over 2, and theta is equal to pi over 2. Okay, and the peak on the backwards is equal to minus y, so it's going to be 0 pi over half, and phi is equal to 3 pi over 2, meaning like, so it's going to be, theta is going to be 90, and the phi angle is going to be this angle, 3 pi over 2. Okay, so let's write our equation. AF ends up, so F4 is equal to 0.9 e to the j 0.2 pi 1 minus sine phi sine theta sine phi plus 1 plus 0.9 e to the minus j 0.3 1 minus sine theta sine phi plus 0.6 e to the minus j 0 point pi 1 minus sine theta sine phi. Okay, so that keeps going to 0.6 e minus j 0 point 9 pi 1 minus sine theta sine phi plus 0.6 e to the minus j 1.2 pi 1 minus sine theta sine phi plus 0.6 e to the minus j 1.5 pi 1 minus sine theta sine phi. Okay, so that's the equation that we are gonna use in MATLAB to derive our plot. And in order to calculate the E-plane, we set up e to 90 or pi over 2, and in order to get our H-plane, phi equals to 90 degrees pi over 2. So in order to get, so this is our equation for the array factor of the yagi. In order to calculate to make your plot, we replace, to get the E-plane, replace that into theta equals to pi over half, and then for phi replace that to pi over half. Okay, and then we're gonna use this in MATLAB to calculate those plots.